Welcome to my channel. I'm Zhan Xu. Let's look at the problem 32 in chapter 28. Chapter 28 is about sources of magnetic fields. This is a follow-up problem for problem 31, and it's a typical application about Ampere's law. So there we can see for this cable we have inner part and outer part. The current density for inner part is given as J1 equal to C1 times R, right? C1. This is we don't know, but we can work it out. And then the J2 is C2 times R, so it looks like we need to find C2 first. And then we need to find the magnetic fields at the four regions. So at the very beginning, we need to determine the constant C1 and C2, right? How can we do that? As we can see, look at the inner part. We see the current goes through inner part is I0, right? And its density is J1. So, and this J1 is changes with R, is a variable with R, right? So that means we can do the integrals, right? So the current equal to the density. Integral, so the density times the cross-sectional areas. Agree? Yes? So this is J1 and we cut it in small fractions. Each fraction is 2 pi r times dr, right? And then do the integral from 0 to r1. And then you solve this integral. And then you will find the equation. Look like this one. Convert this equation, you get the function for C1, right? So we get the constant C1 there. Similarly, we can get the look at the outer part. For outer part, we can say the current goes through is negative I0, right? Negative I0. And then the density times the cross-sectional areas do the integral from R2 to R3, right? And then solve this integral. You can get the equation look like this one. Finally, reorganize it. You get the function for constant C2. Now we get C1 and C2. We can write the charges density J1 and J2 in these two terms. After we get the charges density, can we find the magnetic fields in these four regions? Yes, Ampere's law, right? So now we can see the first case R is smaller than R1, so we can draw the enclosed path. Look like this one, right? So this is B times the path 2 pi r and equal to mu naught times enclosed current. So enclosed current is the density. J1 times the cross-sectional areas 2 pi r times dr and then integral from 0 to r. Solve this equation, you can get the B equal to the term at there. Similarly, for the region R is larger than R2, smaller than R3, it's there. Oh, sorry. So there, if we look at the R is larger than R1, smaller than R2, we can draw the enclosed path at there, right? Yes. And then in this case, we can say we still do B times 2 pi r, this is enclosed path, equal to mu naught times enclosed current. Then you can do the integral, or we can say after integral, you can say the enclosed current just I0. So you get the function at there. The third one, we can say, we use the blue. It is R larger than R2, smaller than R3, so we can draw the enclosed path like this one, right? And then in this one, we can say this is B times enclosed path 2 pi r, and then the first current is inner part, so J1 times the 2 pi r dr, this is the cross-sectional areas, integral from 0 to r1, and then the second part is this part, right? This part enclosed in the outer part, outer cables. So mu naught times J2 times 2 pi r dr from the R2 to R. And then we solve these two integrals. We get function look like this one, and then convert this equation. We get the function for term for B, right? Look like this one. The next part is R is larger than R3. So that means we can draw the enclosed path look like this one. Look like this one. And then we can say this is B times enclosed path 2 pi r, and then this is inner This is the current for inner part, outer part, opposite direction. So add them together, it's 0. So B equal to 0. And finally, we can write the 4 regions, the magnetic fields in these functions. Thank you.